Hello and welcome to an Orcad tutorial on how to implement a silicon carbide based buck converter with the parameters of 500 volt input and 200 volt output with the output current of 10 amps at 500 kHz. In this video, I will be implementing the bootstrap topology. Please watch the part 1 of this series to make sure you have properly imported the components we will be using in this video. First, we want to open up Orcad and create a new project. Go ahead and name your project, select the first option here, and pick a location to save it. Hit OK and click blank schematic. It'll create a new schematic page for you here. From the previous video, we learned that we can just select all of the libraries here. If you don't have this window open, you can just go to place part and it'll pop up. Go ahead and select every folder in your library with Control A and type the part you're looking for. Let's get the gate driver, UCC 21520 DW. We want to avoid using the design cache, and we want to use this one. Double click on it and just place the item. Next, let's find our silicon carbide MOSFET, SCT3160KL. And we need 2 of these guys. 1, 2. Next, we'll need an inductor. So just type L for inductance. We'll also need a capacitor. Let's use all analog components here. We'll also need a resistor. Let's just use a Pspice element. We'll need a voltage source DC, so VDC. We'll be using 2 different grounds. You can actually just hit place ground here. We'll need 2 types, one for the digital side of the gate driver and the other for our power supplies. We'll need this ground, and we will also need ground signal and ground, just regular ground. We will also need a diode, the MR1376. Let's grab the non-design cache one. We will also need another diode, the 1N1183. Lastly, we'll need a digital signal that will provide the PWM signal. So go ahead and just type DIGSTIM1. we'll need 2 of these guys. One for the high drive and one for the low drive. To change the value of this, we actually just need to double click, set the name for it, INA. We'll go back to this later when we set up the simulation, INB. To change the values of these guys, just double click and set your desired value. Same goes for the ground. You will actually get a ground error. So for every single one of your grounds, you will need to change the name to 0. And just close out from this property editor. And it's asking if you want to apply it for all of the grounds that you have, and just click yes. You're gonna want to just copy the one that you just edited to save some time. And same goes for this one. You just want to change this to 0. And exit for save, and they'll again ask to make sure you want to do this, save, and close. And those are the components you'll be needing to create the bootstrap topology. I'm going to populate the schematic and I'll show you how to connect all of these components together. So I'll be back. I've populated the schematic. To start a wire, just hit W, and if you want to exit out of it, you can just hit W again, or you can actually just hit escape. So we're going to connect this to power the gate driver. To the both pin 3 and 8. And we want to connect this ground here. We have a 15-volt input here. We want to keep this ground only on the digital side here. This is just to make sure symbolically we understand that this ground on the circuit side is different from this ground on the digital side here. And we want to put these guys in parallel, again in parallel. We put this one connected to the high voltage PWM input. And this guy to the low drive. You will actually ground pin 5 and 7. Make sure you don't connect those guys. It actually gives you a red warning sign that it's going to connect. Very helpful. Now to set the dead time, and we want to connect this bottom part to ground. Oops. Great. You can again change the values by just double clicking. And that's it for the digital side. Going to our circuit. This is typically how your silicon carbide MOSFETs will be imported as. To get into this format, you would actually need to edit the component here directly. But to show you why the numbering is this way, it's actually in alphabetical order. We have the drain here, 1. We have the gate here, 2. And we have the source here. So I will show you how to change that. Go ahead and click Edit Part. And from here you can just oops, there you go. You can just edit the properties. Let's just name this some arbitrary number for now to avoid duplicates. It won't let you have 2 pins set to the same value. So you want to click on the outside here. Notice if I double click here, there's no change. Even here, but if I click kind of on the outside, try to prompt the box, there we go, and double click. So you want to change this to value 2. Let's change this now to value, do this guy first actually. I think if you just click on the line, it'll let you edit it. And let's change this to pin 3. So there's actually some code behind this component, and no matter how this is configured, it knows which pin is the gate and which pin is the drain and which one's the source. So we're going to go ahead and just save this. Oops. Let us save. Oh, there it is. So we can just hit update current. And it's just going to ask it again, are you sure? And we have it in the same format here. So we'll go ahead and actually use this one. Or replace the one with them. Okay, so I'm going to show you how this is wired up. So we're going to connect the VDDA with the MR1376 diode, have it in series with a resistor, and connected to a power source, 25 volts. And we'll just connect this capacitor. Connected to VSS-A. We want to connect, let's start with the gate. Let's connect the gate to the diode here. And this combination is connected to our it's connected to our out A. And let's do the same thing here. And this is connected to our out B. This is going to be the output signal that's coming from our digital signal on the left side of this gate driver. And it will be fed into the gate. let's ground this resistor. Again, double click on your ground to make sure you named it. You will get an error telling you to name your grounds. I'll just connect this here. And now let's put these guys in series. I'm sorry, parallel. We have a voltage source here. And we're just going to ground this as well. And this is all connected to VDDB. For the no connections, just connect pin 13 and 12 together. And let's connect VSSB to, make sure you don't end up connecting and overlapping with the other wires. You want to make sure this is connected to just this node here. We'll just connect our main buck converter here. Put these guys in parallel. Connect to ground. So we want to connect this is an NMOS. So this is gate, this is drain, this is source. We want to connect the source of this to the drain of our low drive. This is our high MOS silicon carbide MOSFET, and this is the low drive of it. We actually need to connect VSSA to the same node here. We need to connect this resistor to this node as well. And we need to connect this inductor to this node as well. So VSSA to the capacitor. Let's make sure this is connected. Sometimes it's hard to tell. Let's rewire that to make it very obvious it's connected. Also check whether these guys are connected, which they are. Oops. Kind of hard to tell sometimes if they're so close together. This resistor is connected to that node. So is the source, the drain, and the inductor. And lastly, we connect the drain to the 500 volt input. And that should take care of the connections on the right side of the gate driver. Next, we will find the transient response of this. There's a couple steps before we actually get a output on it. So let's walk through that. The first step is to create a new simulation profile. You can just name it simulation 1. Go ahead and create that. Let's see if we get any errors. It'll actually prompt a simulation setting. For this topology, we want to click skip the initial transient bias point. We can just do 1 millisecond. Go to options and hit auto converge. Click on it and hit OK. Next, we have to take care of some configuration files, one for the digital signal and the other for the real components we use. So in order for us to do that, we have to hit Library, Browse, go back to the folder where you where you downloaded the real components, the gate driver and the silicon carbide MOSFET. I saved mine in downloads, so go ahead and select the folder. It will be a .lib file, .lib, and just add to design. And let's browse again. Let's go back to downloads and let's get the .lib file for the gate driver and add to design. Next, we will create a stimulus file. So we're gonna hit stimulus and hit edit, and it will prompt a editor. In this editor, you will hit file and new. Next, you will add a new stimulus. Remember the names that you called the PWM digital signal? We're going to use those references. So we named the high drive INA, and we will make it a clock signal. And we want to be able to set it using the frequency and duty cycle. We selected 500 kHz with a duty cycle of 0.4. And the initial value can be 0 or 1, but you need to make sure that the next one is opposite of it. So we need the low drive digital signal, INB, clock, hit OK. Again, same frequency, 500 kHz. And we want to do 0.6 instead and have an initial value of 1. Now, notice this is how we want the waveform to look like. There is always at least one MOSFET on at any given point. 0 value, 1 value, 0 value, 1 value, and here's the time scale here. You want to save this file. I'll just save it in the general area here and just call it stimulus file. Hit OK. Now that's saved, you can actually close it. Now you need to add that file. You have to remember where you saved it. Public documents. And it's right there. Go ahead and press OK. Add to design. So we added in total 3 files, the real components here, as well as the stimulus file for the digital signal we have here. Hit OK. And let's see if it will run. Go ahead and run Spice here. And hopefully we don't get any errors. Actually, it's canceled this. We actually didn't put any probes on. So let's see what the voltage is here, voltage output, and the current running through this resistor will tell us our current output. Let's make sure that we are getting power as well. So let's put a voltage node here at 500. And we can also take a look at our PWM signal by putting a voltage node there. And let's run the Pspice. It won't actually pop up. You'll have to click on the bottom here. It'll take a while, so I'm gonna just pause this video and we'll see the results. And we're back, and this is the simulation waveform you should get. Let's look at the voltage. The reason why it says R13 is because that's the voltage at that resistor value, R13. And as you can see here, we can just hit the toggle cursor, click on the waveform you want to see. The plots actually come out nicely here. So at some time as it stabilizes and it goes into steady state, we find that the voltage is around 198 and our current output is almost at 10. So we got the circuit working to our parameters. And if we look closely at our PWM here, let's see. Oops. We want to get out the cursor, click again, right click on zoom area. Let's just zoom in here. And we're zooming in on the PWM signal. Again, right click, zoom area. And this is exactly what we want to see. They're definitely overlapping, but there's always at least one MOSFET on. And this is the end of this tutorial on the bootstrap topology. Here is the final circuit if you want to take a screenshot of it. Thank you for watching the video.